Okay, welcome to the last session of the conference. Our first speaker is Johanna Knapp, who will tell about exploring Calabi-Yau moduli space with engaged linear sigma model. Please.
So thank you very much for inviting me. It's a very nice conference, so I would like to join the other speakers to thanking the organizers for doing a really great job. So today I would like to talk about a series of papers that I've written in the past few years in collaboration with Mauricio Roma, Emanuel Scheidiger, my previous PhD student David Erkinger, and my current PhD student Robert Pryor, who will be on the market this year. And the general theme of this talk is going to be, well, exploring moduli spaces of Calabi-Yau compactifications and doing exact calculations and quantum corrections in them in regions which are not necessarily your ordinary smooth geometric Calabi-Yau. So I've been a bit tempted to call this talk strings and non-geometry, but then I did not. So here's an outline of the talk, I hope. Let's do it like that. Now it's working. So today I will be talking about the stringy Kähler moduli space and limiting regions in them. And my main tool of study will be the gauged linear sigma model, which can probe the global structure of the GLSMs. And I want to apply these to regions in the moduli space which are not so well studied. And these are called the hybrid models. And we will do some explicit calculations in this context using GLSMs and other techniques. All right, so the first 3 slides will be a bit of an overview of stating the problem. I guess many of you know that. So the context I'm going to be speaking about will be type 2 theory on compact Calabi-Yau threefolds, possibly with branes, where the branes will be B-branes, because I don't have really much to say about A-branes. And I will be looking at the Kähler moduli space of the Calabi-Yau. And this has lots of structure, and in particular there is a chamber structure in this Kähler moduli space. And of course there are regions that are very well understood, which are the large volume regions. And then these boundaries of the chamber would correspond to the Kähler cone, but we all know very well that we can actually go outside of the Kähler cone, and if we're lucky, we're finding another geometric region via some flop or generalization thereof. But if you go to other limiting regions in the moduli space, you don't necessarily have to find a smooth geometry. So other types of regions which are well studied are, for instance, Landau-Ginzburg orbifolds, which typically arise in stringy Kähler moduli spaces of Calabi-Yau hypersurfaces. And what I want to talk about today is regions that are not like that. So we are still in the limiting region, so I don't want to say anything about the middle of the moduli space, as other speakers have done. But I want to study other limiting regions, and usually they're not very well understood, and I don't think in general we're in a good position. But there are some models which are these hybrid models where we can actually have control over what's happening in the regions. All right, so just to give a little bit of a summary of what kind of questions we can study about these more exotic regions of the moduli space. So the first is how to characterize them both mathematically and physically. So in large volume regions, we know that we have nonlinear sigma models, and we have algebraic geometry, so that works very well. And Landau-Ginzburg models, we are also very well understood. We have actions, we understand branes, and so on and so forth. And other regions, well, they can be quite a lot. We usually don't know what the low energy effective theories are that describe them, with one exception that I'm going to talk about today, which are the hybrids. And then we can ask, if we understand at least a little what the model is in this limiting region, what can we calculate, and in particular, can we calculate quantum-corrected things? So we're in the Kähler moduli space, and in the Kähler moduli are responsible for quantum corrections in all kinds of things that I will talk about a bit later. And in particular, can we, for instance, compute generalizations of these enumerative invariants that we know from geometry, like Gromov-Witten and Gromov-Witten and Donaldson-Thomas invariants. And at least for Gromov-Witten invariants, there is a way to sort of extend this beyond the geometric setting, and this is known as FGRW theory. And that basically computes the analogs of these invariants for Landau-Ginzburg models, and we can generalize that to other types of models as well. And another question that we would like to ask is, what about d-branes? So again, in the geometric setting, we know d-branes quite well, especially the B-type d-branes. They are objects in the derived category of coherent sheaves, and they are very well understood. And also in Landau-Ginzburg theories, we know that d-branes are matrix factorizations, which is a non-geometric formulation. So the question is, what kind of formulation of branes can we have when we don't have a geometry? And it actually turns out that the matrix factorizations in some way are more general than the, let's say, geometric d-branes that we have in the large volume regions of the moduli space. And the GLSM will more or less show you why. And in general, you can ask, we have this moduli space, and we have geometric regions, and we have other regions that look very different. They have very different, physics descriptions. But there's still a connection to it, especially through the gauged linear sigma model. So one can ask, are there any universal objects that you can sort of study, for instance, in the context of quantum corrections, that exist in all the region, irrespective if it's geometric or not? So it should not necessarily rely on standard geometry, but there are things that are universal that can give a hint of what these objects are. And one of them is in the UV, so to say, which is the gauged linear sigma model, which is sort of a UV description of a common UV framework of all these chambers that we've seen. And of course, because I'm in a Calabi-Yau setting, we also have a worldsheet CFT at every point in the moduli space. These perspectives give information about something that is not necessarily geometric. So my main tool today will be the gauged linear sigma model. So just to summarize, there will be more technical summary as well. So GLSMs are 2,2 two-dimensional supersymmetric gauge theories, and we can think about also understand branes in them, and especially B-branes are the ones that I'm going to talk about today. And the reason why the GLSM is useful for these questions is that it comes with coupling parameters, the phi theta parameters, a complex parameter, and they can be identified with the Kähler parameters. So the GLSM sees the full global structure of the Kähler moduli space, and you can study the GLSM at for different couplings, and then you will have a low energy effective theory that corresponds to the limiting regions that we're interested in. And this is called phases of the GLSM. So the vacuum equation of the GLSMs will depend on the choice of parameters, and will lead to different low energy effective theories, and that could be a nonlinear sigma model or a Landau-Ginzburg model or one of these hybrids. So the GLSM has been around for a long time. It recently celebrated its 30th birthday. But what is a little more recent is the fact that from supersymmetric localization, it was possible to exactly evaluate the path integral for certain two-dimensional backgrounds. And it turned out that this actually can compute quantum corrections. In a geometric regime, it's very well understood what they compute, but because the GLSM can access also the other regions, we can use these partition functions to do calculations in regions of the moduli space that are not necessarily geometric. And the object I'm going to focus on today will be the hemisphere partition function, which computes the exact central charge of a B-type D-brane. We will use this to study these hybrid theories, which will be part 3 of my talk. So what I would like to do next is to introduce these quantities and the GLSMs a little bit more, and to see how and what we can get out of them. So it's a gauge theory, so we'll need a gauge group, and even though I wouldn't have to do this restriction for today, I will have abelian gauge groups, but there's a lot of activity also going on for non-abelian GLSMs. I will not introduce the full theory, so these are nice theories. They have Lagrangians, you can write them down, you can write down supersymmetry variations. I will only introduce the scalar sector because I'm mostly interested in the vacuum, and I only need the scalar degrees of freedom to give you the definition of these partition functions. So we have a chiral multiplet and some complex scalars, and also the anti-chiral multiplets, of course, that take values in a vector space. They are charged under the gauge symmetry. I call the charges Q. And there is axial and vector U1 symmetry. The axial symmetry is broken unless we impose this condition here, which coincides with the Calabi-Yau condition. So this is how a GLSM becomes a Calabi-Yau. It's a restriction on the gauge charges. And there is a vector R symmetry, and these are the R charges with respect to the vector R symmetry will play a role in the definition of the partition functions. So it's a gauge theory, so we also have vector multiplets and their corresponding scalars. They are just Lie algebra valued fields with respect to the gauge group. And as I said in the beginning, I'm going to talk about compact Calabi-Yaus. And in order to model compact Calabi-Yaus, you also have to choose a superpotential in the theory, holomorphic function in the phis. It's gauge invariant, and it's supposed to have a fixed R charge, which I will choose to be 2. And that's basically the setup that we need. And then we have the Fi theta parameters, which we will identify with the Kähler moduli. Okay, and the first thing that one does in this context is we study the vacuum structure. So we have to find the zeros of the scalar potential of the theory. And this is what it looks like. I haven't written out the D-term and F-term equations completely. They come on the next slide. So basically, it has a complicated vacuum structure. There can be Higgs branches that are dominated by the chiral scalars, and there can be Coulomb branches dominated by the sigma fields, and all kinds of mixed branches. So finding the vacuum of a general GLSM is not a non-trivial task. So for the sake of today, I will only be interested in the Higgs branches, which determine these phases of the gauge linear sigma models. So I will set all the sigmas to 0, so all I'm left with solving is the D-term and the F-term equation. By the way, the E is the gauge coupling. I hadn't introduced that yet. Okay, so how to see this chamber structure and these phases that I had on this picture from the GLSM perspective. So we're setting all the sigma fields to 0, which in the abelian case at least puts us on the Higgs branch. And then we have D-term equations and we have F-term equations, which have a standard form. So this is the D-term equation for the U1, for the abelian case. For the non-abelian case, you have some moment map equation appearing. So what's to be noted here is that the D-term equation depends on the Fi parameter, which is basically the real part of the Kähler modulus. So that means the solutions to these vacuum equations will crucially depend on which choices we take for the zetas. And this is what gives us the chamber structure, so formally, and the phases. So formally, we can just write the solutions depending on the parameter, on the Fi parameter, as the formal solution to these equations. So I will not go into details about examples here, but rather move on to the branes, because I want to come to the hemisphere partition function. So B-branes and GLSMs have been worked out by Herbst, Torrey, Page in their 265-page paper from 2008, and in the non-abelian case by these authors in the context of deriving the hemisphere partition function. And in the GLSM, a B-type D-brane is a matrix factorization. So that's a set of data. We have some module which we can understand as a Cham pattern space for the branes, and it naturally comes with a set 2 grading. And then the brane is characterized by a matrix factorization, which is an odd endomorphism on this Cham pattern space. So you can think about this is very explicit. So you can think about this as a square matrix of polynomial entries in the scalar fields. And whenever this matrix squares to the superpotential times the identity, you're describing a D-brane. And we also have the gauge symmetry and the vector R symmetry acting on the D-branes. So gauge invariance implies that the matrix factorization itself is invariant, and R symmetry implies through this matrix factorization condition that the matrix factorization has to have R charge 1. And this is also very explicit. You can compute these charges just as matrices. And these two matrices, rho and R star, that give the gauge and R charges of this brane, they will play a role in the hemisphere partition function, and I can give the definition of this now. So the hemisphere partition function comes from supersymmetric localization. So you take the GLSM, put it on a hemisphere, put the B-brane on the boundary, and you realize that you can evaluate the path integral exactly. And here it localizes on the Coulomb branch. So in the end, what you get after a long calculation is an integral just over these chiral scalar fields. Gamma here is a middle dimensional integration contour taking value in the Lie algebra. And most of the data I have already defined here. So alphas is just for the non-abelian case. These are the positive roots. Q's are the gauge charges. These are the R charges. And crucially, the Fi theta parameter enters in here. So this is a complex contour integral, and gamma functions have singularities, and we have an exponential factor here that determines the convergence. So depending on the choice of phi theta parameter, which means the choice of chamber in our moduli space, or region in our moduli space, this integral will pick up different poles from the gamma functions and give different results in different phases. So we have a means from the GLSM to compute something about the D-brane in these phases. And the information about the brane itself only enters through the gauge and R charges that you can compute through the conditions that were on the previous slide. And the good thing is that the objects it computes is actually very useful. It's the exact central charge of the B-brane. So that means the leading terms are the Ramond-Ramond charges of the brane. And then we have all the sub-leading terms coming from instanton corrections if we have an interpretation of instantons like in the geometry. So this is a very useful object to compute. And what we would like to do is to sort of evaluate these partition functions in this lesser studied region of the moduli space and learn something about the quantum corrections and the theories that are in these limiting regions that are, let's say, not geometric or not Landau-Ginzburg. This is where these universal structures are coming in. So what we've advertised in papers and tested for Landau-Ginzburg and Calabi-Yau and then sort of conjectured to be true more general is that when you evaluate this hemisphere partition function in a given phase of the GLSM, so if you go to a specific region, a limiting region of the moduli space, it has a universal structure in terms of objects that can be determined by the data associated to the corresponding phase. So what you see here is a pairing. This is a pairing on the state space of the CFT. And because this is more or less the A model sides, the associated corresponding states are those of the AC chiral rings. You have a topological class associated to the gamma function, which is the gamma class. You have an I function, which more or less encodes all these e to the t corrections. And we don't need mirror symmetry for that, but if we had mirror symmetry, the I function would coincide with the periods of the mirror. And we have a Chern character of the brane. So in geometric and Landau-Ginzburg phases, all these objects are known and defined, so we can take examples and check that this formula is really true, and this is what we did in the first paper. But what we can also do is when we have a phase that is not so well understood, we can just evaluate that, rely on the structure, and then extract at least conjectural results for what the I function, the Chern character of a brane or something is, or even the structure of the state space. And all these objects can actually have a definition also without reference to geometry. Of course, when you have geometry, it will be with respect to the I function will be a vector expanded in terms of the cohomology of the Calabi-Yau, but you don't need that. You also have state spaces in other models. All right, and this is what I plan to do for these hybrid models. So now finally, I want to give you a slide on what these hybrid models actually are and what they generalize. So the structure you have is a non-compact space. So you have a compact base manifold, so you can picture that to be a PN, for instance, and you fiber some rank n bundle over it. And in addition to that, you choose a holomorphic function, which will be a superpotential that is subject to the condition that its critical set is this compact space. And the hybrid model itself is a nonlinear sigma model on Y. So it's on a non-compact space, so I can put a superpotential on it. So it's a nonlinear sigma model with potential, and the potential more or less makes this still into a compact space in a given sense. And you have to put some extra conditions on it so that the CFT in the IR is well defined. And this makes this actually quite constraining. And Bertolini, Melnikov, Plesser, who wrote a paper in 2013 to really understand these so-called good hybrid models from the level of a CFT perspective as well. Well, they call it good hybrid. Everything else would be a bad hybrid. And my fear is that the bad hybrids are the ones that are the generic limiting regions in this moduli space. But these have well-defined IR CFTs, And the bulk state spaces and the bulk theories of these theories have been worked out by Bertolini, Melnikov, and Plesser. So at least the state spaces on the previous slides, they were understood. And I should also say that this generalizes examples that are better known. So for instance, if you take B to be a Calabi-Yau threefold itself and set the potential to 0, you recover a Calabi-Yau nonlinear sigma model. And on the other hand, if you choose B to be a point, with a non-zero superpotential, you recover a Landau-Ginzburg model. So in that sense, it's a more general structure. And another important thing is that hybrids arise as phases of well-studied Calabi-Yau GLSMs, so we can also make a connection to the geometry via the GLSM. So here's one example that is actually very old and very well studied. The people who know toric geometry will recognize that. So this is a two-parameter GLSM with 2 gauge groups, and these are the phi fields. They are labeled with the knowledge what the geometry is. We have 2 Fi parameters, and there is a geometric phase when these Fi parameters are large, and that's just a well-studied 2-parameter Calabi-Yau hypersurface in the toric variety defined by the weights of these fields. There, it has Hodge numbers 286. It's one of the earliest 2-parameter examples where mirror symmetry was studied. So for the experts, they will also see that this has an additional structure. So this is a fibration. So this is a P1 base manifold, and we have a K3 fibered over this. So what we can do now is we can take the first Fi parameter to negative infinity or to negative values so that the K3 fiber undergoes a Landau-Ginzburg transition. And that gives us a hybrid phase, as already Morrison and Plesser pointed out to us in 94, so that's not really news. And this really fits the setup. So we also have we actually have a Landau-Ginzburg orbifold, which comes that the first U1 is breaking to a set 4. So we have the total space Y that I had before is this bundle here. This is deduced from the weights of the second line, fibered over P1. The fiber coordinates are x3 to x6, and the base coordinates are x1, x2. One of the results in the paper from a few weeks ago was to actually, before coming to the GLSM, study brains in this hybrid model. So the bulk theory was understood, but also hybrid models. They are nonlinear sigma models with the potential. So we can actually derive in the hybrid model what a B-type D brain is. And it turns out that it's a hybrid between a geometric brain and a matrix factorization. So this result here that really comes from writing down an action, putting on a boundary, enforcing B-type supersymmetry, and see what kind of conditions we get to maintain B-type supersymmetry on the boundary. So a B-brain in a hybrid model is this set of data, and it's very similar to the B-brains of a GLSM already. And that's also what I said with matrix factorization being more general than coherent sheaves, for instance. So you have a set2 graded vector bundle on this non-compact space Y, together with a connection of curvature type 1. Together, these two things make up a holomorphic vector bundle on Y. We also have a matrix factorization, just like we have here. They are called global matrix factorizations. And it's also all the structures compatible with the orbifold and the R symmetry actions that we have in the hybrid model. And the constructions themselves, so this is very explicit again, you can construct many brains and many models. So what you have to do is, because you have a fibration over a compact manifold, you actually have to construct this patchwise. So you have like a fibration over P1 as in the previous example. So you take a local patch on P1, construct a matrix factorization there, make an ansatz for the data of this bundle, and then sort of gluing the patches together actually fixes the bundle, the gauge information, in most cases, and you can just characterize a brain like that. And many known construction of geometric and Landau-Ginzburg brains very readily generalize to these hybrid models. So we have a geometric type brain in the base and then a Landau-Ginzburg type brain in the fiber. So that all works very well. And now I can go to the GLSMs. So one thing that we do not know yet is, for instance, the churn characters of the brain. So they are not really geometric, so we would like to have some information of what they are like. I mean, there is intuition, but we would like to find that. So there are ways to compute that, but sort of an easy way to learn more about these brains is to actually lift them to the GLSM, which is something that we know or that we can do, and then use the hemisphere partition function to sort of infer information about the Chern characters. So we take the general structure for granted, guess that this brain factor reduced to the phase is actually the Chern character of the brain. And then we are sort of in business because we can sort of decide, what is a basis of brains, because we have the charge lattice that we can get out of it. And we can also, thanks to Herbst, Torrey, and Page, make a connection between geometric brains and these new hybrid brains. So basically what we did is we constructed a basis of geometric brains, used Herbst, Torrey, and Page and the hemisphere partition function to transport that to the hybrid phase, and evaluated the brain factors which we identified with the Chern characters. And at the same time, we could also construct a basis of hybrid brains with the structure that was on the previous slide, do the same business and obtain the Chern characters, and then sort of compute the sort of transport of the hybrid brains, of the geometric brains into the hybrid phase. So the B model calculation of that would be compute the analytic continuation of an integral basis in matrix of an integral basis in the hybrid phase and the large volume phase. And we are happy that this matrix here can actually be inverted over the integers, which also implies that we've constructed a minimal basis of brains. I will not write down explicit matrix factorizations because these are fairly complicated structures, but these are all explicit examples of brains that are, at least in the hybrid phase, straightforward generalizations of well-known Landau-Ginzburg and geometric brains. All right, and since I have a few minutes left, I can also go to my last slide to talk a little bit about the results of this enumerative invariance that is from a bit earlier. So as I said, with this general structure of this of the hemisphere partition function, we can read off the I function, which is basically the periods. And what one would do when one has periods is one applies mirror symmetry. So we are already in the A model, but there are alternative ways to get that. So if there is another object called the J function, which plays a role in Giventhal's mirror construction, and it is related to the I function that we have access to via a coordinate change, which in mirror symmetry would be the mirror map. But we want to get the mirror map directly out of this A model information. And we can actually do that by understanding the CFT state spaces of this theory, which thankfully for hybrids was done by Bertolini, Melnikov, Plesser. And we have a proposal on how to extract the information about this coordinate change from components of the I functions related to certain CFT states. So the I function itself is a vector expanded in terms of a basis of these bulk states. So we can do a transformation. We can read off the I function and get this change of coordinates and then get the J function. And the J function is the generating function of these invariants. And thankfully, Wolfgang gave his talk yesterday and gave the right interpretation of this invariance. So we have, it's not like enumerative invariance because the enumerative problem is not a priori clear when you have these things, but the invariants themselves, they are genus zero correlation functions of this two-dimensional topological field theory coupled to topological gravity. And this is also how this J function is expanded. And just for the example I had before, this is what these correlation functions look like. So we have some states here, and these hybrid states carry two labels. First one is the twisted sector associated to the Landau-Ginzburg fiber state, and the second one is a cohomology from the base element. And because it's a fibration over P1, we only have like the identity and the hyperplane class. And so one of these states is like a geometric operator, so we can have an instanton wrapping around the base. So we can simplify those a little bit and insert this into the generating function and get some numbers. They are not integers, they're not expected to be integers, and that would be the generalization of the Gromov-Witten invariance from the sort of geometric phase to the Landau-Ginzburg phase, to the hybrid phase. All right, I should wrap up. So just a brief summary. What we've done, we've studied hybrid models by means of GLSMs and hybrid theories themselves. We constructed B-branes in hybrid models. We used the universal structure of the hemisphere partition function to extract information about the hybrids, quantum exact information. So like B-brane charges and genus zero invariance. And using the GLSMs, we could also establish a sort of hybrid Calabi-Yau correspondence in generalization of a Landau-Ginzburg Calabi-Yau correspondence by making a connection between geometric and hybrid branes and computing analytic continuation matrices. So one slide of outlook. So there's a lot to be done because these hybrid models are not really well studied. So irrespective of the GLSMs, there's a whole A infinity category and n equals 1 brane superpotentials that one should actually be able to compute. I sort of did a dirty trick to evaluate Chern characters by lifting it to the GLSM and reading it off from the hemisphere partition function, but there should also be a generalization of this by finding something like a Kapustin-Lie formula for 2 and 3 point correlation functions in these hybrid models. There should also be boundary CFTs associated with these branes, which are not very well understood, or not understood at all to my knowledge. There is some work by the group around Thomas from the B model side of finding integral basis for hybrid theories in the one parameter case K-type models. And yeah, we should be able to clarify that. Also, the hybrids themselves, they are not classified. They should be of an order of magnitude of as many as Landau-Ginzburg theories in this whole list of Calabi-Yaus, maybe. And yeah, the GLSMs themselves also have some work to do. So for instance, there is deep brane transport in non-abelian GLSMs to be studied, because also the non-abelian GLSMs have hybrid and more exotic phases where we very often don't know the mirror. So this is actually the main thing to do, but we still need to understand these correspondences better. And another technical problem is that the GLSM doesn't see the full state space of the theory. So the CFT has more states than the GLSM see, and that's a bit of a bottleneck in these calculations. All right, that's it. Thank you for your attention.